of, we have to find scalar product of those two vectors. What was it? 1, 1, 0, I think, and 0, 1, 1. And then we have to divide it by product of magnitudes of those two vectors. All right, so it's arc cosine. When we calculate, when we know scalar components, well, actually, for those arrays, we multiply first number by first number, add second number by second number, and add third number by third number. So it is 0 plus 1 plus 0. And in the denominator, to find magnitude, we have to square the first component, square the second component, square the third component, add them, and take square root of that. So it is 1 square plus 1 square plus 0 square times square root of 0 square plus 1 square plus 1 square. So it is arc cosine of 1 over square root of 2 times square root of 2. So arc cosine of 1/2. 1 cosine of 1/2 is 60 degrees. Now let's take, this trick is actually quite important in physics, chemistry, electronics, and even and computer science. What I calculated something which was a problem very similar to a problem which was assigned. Because now let's try to find out an arrow, arrows which are assigned to these two. If I draw a coordinate system, say x, y, and z. Okay, 1, 1, 0. It is an arrow along diagonal of this plane. 0, 1, 1 is diagonal along this one. So really we are calculating this angle over here. Now you have to imagine it three-dimensionally. So it will be like, if I consider a corner, that corner over there, the question is what's the angle between diagonal of the floor with diagonal of the wall over here. Yeah, this angle over here. Oops, like that. It's 60 degrees. It's inclined, so it's not that easy to see. Okay. Right, so let's go now to the lecture. I want to talk about application of vectors to physics. Well, last time we finished the lecture with introduction of position vector, and now I'm going to continue. In general, position, if we think about a particle and where the particle is with respect to the rest of the universe, we can say that it is changing its position. Particles do not maintain in a single configuration forever. If they did, then we wouldn't have to concept of time even. So, because configuration changes, we have time, and position of a particle in a universe in general is dependent on time. The difference of positions of a particle at two different instances is called a displacement. So by definition, let's say that at particular instant t1, a particle is somewhere here, and at another instant t2, particle is over there, then difference in that position is referred to as displacement. Well, to positions we assigned a vector and an array of numbers. Therefore, to displacement we can assign a vector and an array of numbers. Well, think about how to subtract now these two vectors, because this is what we have to do. Recall that the subtraction is really addition of a vector which is opposite to this one. So here to this vector, I have to add a vector which is opposite to this one. Well, if I do this, really I will get a vector like that. So if we think about how to assign an arrow, if we didn't do it through this definition, formally, we can have a shortcut that a displacement is an arrow which connects the location of a particle at the, let's say, initial instant, and with the head at the location of the particle at the final instant. I don't like actually to use, we use words initial and final, although more precisely I should say at one instant and another instant, because people get confused. What does it mean, initial and final? Final looks like it is the last possible, so it is at the last instant when the universe exists, and initial, people think that it is when the universe was created. It's not like that. Initial is referred to an instant which we think that we start observing universe or a particle, and the final is whenever we lose interest in the particle. Right. Now that they consistently actually, yeah, because now, let me refresh your memory about something. How many positions a particle had at a particular instant? Just one, correct. How many arrows could we assign to that position? Infinite numbers. By choosing the reference differently, the origin of the coordinate system, we can choose this origin in an arbitrary way, so we can assign a lot of arrows. So actually, over here, now that I use a full arrow, which I refer, over here. So I refer really to the location, to position. On the drawing, you have arrows representing position, and with bars, I would mark the arrays representing position. So for the displacement, formally displacement is a difference in location. So how many of, well, actually it happens now that no matter how I choose, is it true or not? No, it isn't true, although it is not as obvious. I can only have one change in position. However, I can recognize that I can assign a lot of arrows. And I can only assign it if a lot of arrows, depending on this, how the origin actually moves. Because, for example, like if I look at the tip of a finger and I go from here to here, I would assign a zero displacement. You would not assign zero displacement. From your point of view, the finger moved from this location to this location. From my point of view, it didn't. So I assign one difference, you will assign different difference. All right. Now, before I introduce the next physical quantity, and actually I wanted to introduce concept of velocity, I want to make a certain digression, mathematical digression, in which I would like to first, those of you who had calculus, so for those of you who had calculus, I would like to make a refreshment about derivatives. For those of you who didn't have calculus, I would like to introduce it to you. and for both who had calculus and who didn't have calculus, I would like to generalize derivative to vector functions. Because if you had calculus 1, you had a derivative of a number-valued function on numbers. Position is not a numbered value of number. It is a vector-valued function on not vectors, numbers, because it depends on time. Time is a number. So let's start with the concept of a derivative of the function. You have it. So actually, what you have to study is now is appendix. You will from the book. So let's say that I have a certain function, and in order not to confuse it to position with time, I introduced a strange symbol for the variable. It's a Greek letter xi. I doubt that you associate xi with anything so far, like t or x. Therefore, you will probably comprehend it better. So let's say, and I made a plot here of the function. It's just a fragment of the function. Xi is the variable. F of xi is are the values of the function. So for this value of the argument, I will have this value of the function. Derivative, well, actually Newton found the necessity of developing calculus because of physics. Actually, his physics laws are described in an article which has mathematics in the title. This, what you see here, is a formal definition of derivative for a number value function on numbers. So let's see, actually, what do we have to do? We have to calculate difference. If I calculate derivative at a particular argument xi, first what I have, so let's say that at this point I try to calculate the derivative of the function. What I have to do is to see the difference between a point which is in the vicinity of point xi, separated by value delta xi from that argument, and subtract the value of the function at the considered point, and then divided by the difference in the argument. That quotient is called the difference quotient. Say it, shout. Difference quotient, correct. So how about if you imagine it? Yes, so let's say that I pick a certain delta xi. I see what is the value of delta xi. So I get it over. I get that value over here. So this difference is represented by that vertical arrow. So it says by how much the function changed when the argument changed by delta xi. And then I have to divide it by the change in the argument. So geometrically, if you look at this picture, well, I have to divide this distance by this distance. Well, so I will get actually I can imagine a triangle over here, and difference quotient would represent the tangent of the angle in this triangle. I didn't draw actually the hypotenuse of the triangle. So imagine that I draw hypotenuse, then difference quotient would be equal to the tangent of that angle on this side over here. Well, but this is not what derivative is. Difference quotient is not the derivative. We have to take that change between xi and delta and between the two arguments smaller and smaller and smaller. We have to bring this point closer and closer and closer to value xi. And when so that way we will get a sequence of numbers. For every delta xi, I will get a certain value for difference quotient. Now I have to take this delta xi getting smaller and smaller and smaller, so the difference quotient will form a sequence. And to whatever number that sequence is going to converge, this is the value of the derivative. Well, if I recognize actually the difference quotient was the tangent between hypotenuse of this triangle and the horizontal line, then I can recognize that if I take this point closer and closer to xi, eventually, I could write it down also that it's limit of the change in the function over change in the argument. And if I take this value, I can recognize that it represents the tangent of the slope. I mean, the slope of that line, which is tangent to the plot of the function. However, I don't want you to take the slope as the definition of derivative. I know that some of you think that the derivative is the slope. No, it's the other way around. Slope is equal to the derivative, but slope is not the derivative. Make sure to distinguish phrase is with is equal to. These are two different things. I know, we use very often is as a substitute is equal. So for example, if I say that my height is 6 feet, so what do we understand by is?
Your height is equal to 6.
My height is equal, because my height is the difference in elevation or distance from the top of the head to the bottom of the feet. This what height is, but it happens that the distance is equal to 6 feet. All right. If we have a vector valued function, we calculate the derivative in exactly the same way. However, the geometrical interpretation won't be now that it is a slope, because we cannot plot this function. We cannot plot a vector function because vertical axis, on the vertical axis we can only plot numbers. However, we take again limit of this quotient. Shout, what do we call this quotient? Difference quotient, correct. So derivative is equal to limit of the difference quotient. Now, let's say that at instant xi, value of the function is represented by this arrow, and then argument xi plus delta xi, it's this arrow. So what would be the difference between these two? Consult with each other. Can you imagine the difference between these two? If I subtract now vector f of xi from vector f of xi plus delta xi, what am I going to get? A what? Delta f, but where should I mark it? What am I going to get? Am I going to get a number or a vector when I calculate the difference? A vector, correct. All right. Now, what will be the direction of that vector? A what?
The same direction as the psi plus delta psi.
The same direction as this vector, which means that the difference is going to be in this direction. Who agrees with, what's your name? Jessup? Justin. With Justin. Who disagrees with Justin? Those of you who disagree, you are right. What would be the difference according to you? The opposite direction as this vector, right? So it will be that way. Who thinks that it's going to be this way? Who thinks that it's wrong as well? Those of you who thinks that it's wrong, you are right. What about you?
I think it'll be from the head of psi plus delta psi to the function of psi.
So, what's your name?
JT.
JT thinks that it will be an arrow from here to here. Who thinks that JT is JT? That JT is right. Who thinks that JT is wrong? Those of you who said that he is wrong, you are right. What do you say? Oh, so why did you say that he is wrong? Not a good argument. Oh, you have an idea? Well, how about if we do it on the whiteboard? So this vector is f of psi, and this vector is f of psi plus delta psi. All right. So what am I supposed to do first?
Subtract.
Well, yes. But subtraction is really addition. Yeah. So I have to flip one of the vectors. Which one? This one. I have to flip this one, and so it will be a vector like that. Now what do I have to do with that vector? Bring it there, right? Okay. Yeah, so this vector is minus f of psi. And now what am I supposed to do? Right, but how am I supposed to draw that resultant vector from the tail of which to head of which? Correct. From this tail to here. Right? So I could mark it over there as well. Which means that the difference of these two vectors is this vector delta f. Well, now I have to divide it by number delta psi. What am I going to get? Think that delta psi is a small number. Let's say that delta psi is 1/10. No, let's say 1/2. 1/10 is too small. Let's say 1/2. If delta psi is 1/2, what will be the value of the difference quotient? Twice what?
Twice the magnitude.
Well, the result cannot be twice magnitude, because twice magnitude is going to be a number, not a vector. But TJ, right? JT. But JT is on the right track. Magnitude of the new vector will be twice as large as this one. So it will be 2 times longer. Now heading which direction? The same as that arrow, correct? Yes, so we will have difference quotient is going to be in this direction. And all of those difference quotients are going to be in this direction. We will get a sequence of vectors, and we have to calculate limit. When we calculate limit of it, then we are going to get the derivative of a vector valued function of single variable, I mean number valued variable. So derivative of a vector function of one variable is a vector or a number? A vector, correct. Before actually I go, I want now to introduce 2 more things. One is, I mean, these are concepts which are very useful. They were introduced by Leibniz. So rather than thinking in terms of difference quotient, let's think about infinitesimally small changes. So formally, the differential of a function is defined as a product of the derivative of the function multiplied by an infinitesimal change in their argument. Infinitesimal means teeny tiny, very small change. So here we have a very small change of a function due to a very small change in the argument of the function. It is valid only for certain type of functions. Function has to have derivative. So the function has to be continuous and smooth. Physics, fortunately, has mainly those functions. In math, you have a lot of functions which are not like that. In physics, physical quantities are represented by nice functions. Let's now take a look at the geometrical interpretation of a differential. It's very similar actually to a difference of a function. So rather now than thinking about the change in argument, think about tiny change in argument. Now tiny change in argument is like going from, let's say if I consider about time, so it will be something like considering 2 consecutive instances. Now problem is that between any 2 consecutive instances you can find another instant, right? But think that you continue it until you cannot do it. At that time you will get an infinitesimal change in time. Now if I walk, for example, so it is from my position to the next available position in space. Now here is again a problem that between 2 points I can always put another point. When you think about differential, think that you continue it until you cannot put another. So develop this abstract thinking. Now, according to the definition, I have to take the slope of the function at this point and multiply by the change in the argument. So really, differential of a function will be a difference between this value and this value. Not like difference quotient, when it was between this point and this point. Yeah, difference quotient took this change in function. Differential takes this change in function. However, when you think about limit of the difference quotient, you see that they are going to overlap. So you can take this interpretation of a differential, that the differential that the differential of a function is the infinitesimal change of the value of the function due to the infinitesimal change in the argument of the function. And it does not matter now if the function is a number-valued function or a vector-valued function for our purposes. In more general case, it doesn't matter what are the arguments and what are their what type of quantity are the values of the function and what are the arguments. All right. Well, so note that from the definition of the differential, derivative of the function is equal to the quotient of differentials. And I think that in calculus you will learn how to use this, and in physics as well. I will more frequently use this notation for derivative, which is referred as Leibniz notation than Newton's notation. So we will represent derivatives as the quotient of differentials rather than f with prime. I want you now to learn properties of derivatives, and I advise you to memorize it. It's really very good to memorize them. They all are listed in the appendix. All the material which I'm presenting here is in the appendix of the textbook. So, when we calculate the derivative of a sum of 2 functions, let's say that I have 2 functions. I use the same formulas. I switch now from xi to x to be consistent with the book. So if I have 2 functions of a certain variable x, I have function g of x and h of x. If I calculate the derivative of the sum, it is equal to the sum of derivatives. So, for example, if I want to calculate derivative of x squared plus x, in the tables you can find out the derivative of x squared is 2x. Derivative of x is 1. So, derivative of x squared plus x would be 2x plus 1. Correct. If we have a product of two functions, we use a formula which is referred to as product rule. So we take derivative of the first function and multiply by the second function and add the first function multiplied by the derivative of the second function. Here I'm not consistent with the book actually. I want you to learn it that way, not like you have it in the book, because the book uses it only for number valued functions on numbers. Product formula is valid for product of numbers, product of scalar product of vectors, for which actually both formulas are good, this one and the one in the book. However, we will learn soon a fourth multiplication. We will multiply vectors using so-called vector product or cross product, and that product is somewhat different. I mean, the major difference of vector product from the other three is that that product is not commutative. When you change the order of the factors, you will get a different result. Yeah, because if you think about numbers, 2 times 3 is the same as 3 times 2. Now if you take a scalar product, vector I times vector j, a product of vector I multiplied by vector j using scalar product is the same as multiplying vector j by vector I. However, if I use the vector product of vector I and j is not the same as product of j and I. We will see that they will be opposite. We will get opposite values. So if you learn the formula that way, then you will be able to apply it to all four products. The one which is in the book is applicable only to products which are commutative. Now that one is referred as a quotient rule. You don't have it in the book. It's not listed in the book. You would have to actually assume that you take function, that you have a product, because quotient is really a product. You multiply function g by function 1 over h, and then you can use product rule. However, it is often useful to know how to calculate derivative of a quotient right away, so I suggest that you memorize it as well. Now you take derivative of numerator multiplied by the denominator and subtract numerator by the derivative of denominator, and then you divide the difference by square of the denominator. And the last rule, which is referred to as chain rule, it is applicable to functions which are called composite functions. So I want you now to shout that chain rule is applicable to composite functions. Say it. Good. Yeah, so now if we have a function of the argument, like for example cosine of x squared. How do we calculate cosine of x squared? What if I let's say that I take, I have a certain value of x. What do I have to do? First I have to square x. Then you have to take a cosine, right? So function h would be square and function g would be cosine. So well, how about if I calculate it on the whiteboard? Let's take derivative of cosine of x squared. So derivative with respect to x of cosine of x squared. So first I have to take derivative of external function. And the external function is the function which we perform at the very end. It's like g, right? So what would be the external function here? Cosine. Anybody knows what is derivative of cosine? If not, you have it in the tables. So, but I know that majority of you had already calculus. So derivative of cosine is negative sine. So we'll put negative sine. And what should be the argument according to that formula? X squared. Correct. We have to calculate the derivative with respect to the argument. So it will be cosine of x squared. Now we have to multiply by the derivative of internal function. And derivative of internal function is already with respect to that most inner variable, so with respect to x. So what will be the derivative of internal function? 2x. Very good. Let's go back to physics. Now when we understand how to calculate the derivatives, we can introduce concept of velocity. And well, by definition, velocity is derivative of position with respect to time. Whenever we calculate derivative of a time-dependent function with respect to time, we call it something. Some of you may know. Yeah, let's say if we calculate, well, let's say that you deposit, that every day you deposit $5 to your checking account. So you will get a function which says, how about if I draw this function, which represents the balance on your checking account versus time. So, at the very beginning, you will have 0. After 1 day, you will have 5. After 2 days, you will have 10 and 15. Right? So I can imagine that actually with time, it grows like that. Right? So if I squeeze now the days so close, this is how the plot. I mean, you could imagine actually that this is balance in between. Well, if I calculate derivative of this function, what am I going to get? Horizontal, right? Of what value? 5, correct. What would we call this 5? Oh, this is $5 per day. This is the derivative of the balance. Well, no, it's not instantaneous rate of change. Well, how about if I just tell you? We call it rate of change. Rate at which you deposit money. $5 per day would be the rate at which you deposit money. Now, you have income, for example, certain income, with annual income. It's also rate at which you are making money. And whatever actually, if something changes with respect to time, whenever you calculate the derivative of it, you will have the rate of change of this function. And actually I wrote it here. Yeah, the rate at which particle is changing position is called velocity. Now, well, so when we calculate the derivative, imagine that I have a position, I mean, how do we calculate it? I have to know the position at instant t plus dt. Now I put it at an infinitesimal time, so it will be something like 2 consecutive instances. Therefore, these are 2 consecutive positions. You have to imagine it as 2 consecutive positions to have this differential displacement. Well, if I divide now this differential displacement by differential change in time, which is a tiny number, I'm going to get what? A vector or a number? Faster. Vector, correct. What will be the direction of this vector? I already asked you this question earlier. And JT was right. No, he was close to right. I think that now you can be right. Well, oh no, I didn't ask. No, I didn't ask anybody. No, I asked just for the difference. So we already have that answer. Now, recall what happened when we multiplied the difference by a number. What did we get then? A vector heading in which direction? Same direction as the difference, right? Therefore, this vector over here, vector representing velocity, is going to be in the same direction and as this differential change in position. So velocity is going to be in this direction. Velocity is always going to be tangential to trajectory. Although you will have to think about this 3-dimensionally, so obviously you cannot say that it's a slope. Yeah, because I can walk like that. Right? And up and down on top of it, and there is no slope of that trajectory. Note, and actually I know that at this moment you thought in terms of arrows, and I want you to develop that intuition, because we never really imagine physical quantities. We better imagine arrows which we assign to these quantities. So although formally the velocity is defined as the rate of change in position, when you imagine it, think about arrows. When you perform calculations, use arrays. All right, next physical quantity is a rate at which velocity changes. This rate is referred to as acceleration. Are you getting scared with that? What that shaking of the head meant?
I just feel like we go through this a little too quickly. That's just my opinion. I just feel like we're covering a lot of topics in like 5 to 10 minutes that need a little bit more time.
Well, okay. So after I finish it, we will take a look at example. All right? Yes. And besides, every time when I introduce, I repeat analysis. So I hope that actually it is going to help. Yeah, because now, well, I want to repeat. I mean, to develop this imagination, considering velocity. So let's say that particle over here had such velocity, and over there it had such velocity. Let's try to figure out what arrow would represent now acceleration. Now, so in how about you? Can you now say in English, what do you understand by this symbol, dv?
The derivative of
No. Derivative is already that quotient of differentials, just the numerator.
the displacement?
Not displacement. Displacement was when we had position. Yes, so if we had dr, then it represented infinitesimal change in position. Now we have dv, which means that it is a what change? Of velocity. What change of velocity? Infinitesimal. Shout it, guys. Infinitesimal change in velocity. Correct. All right. So how about if we imagine now this infinitesimal change in velocity? Well, in other words, we have to, whenever we calculate change, what do we have to do? How about if we think about change in our checking account balance? Let's say let's say that yesterday I had $80 on my checking account and today I have $60. What is the change on my checking account?
60 minus 80.
Negative 20. Correct. 60 minus 80. All right. In general, how do we do that? Final value minus initial value. All right. This is final value of velocity. This is initial value of velocity. Right? So I have to find a vector opposite to this one so that I can subtract it from that one. So if I write minus this one, I will get an arrow like that, and then I will add this vector, so I will have to bring tail of this arrow to the head of the first arrow and connect the tail of the first one with the head of the second one. So here this green arrow represents what? What's your name?
Josh.
Josh. What that green arrow represents? What change in velocity? No, infinitesimal change in velocity. Correct. Now I have to divide it by that small amount of time in which it happened. What am I going to get? A vector. Correct. Heading which direction? In the same direction as the other one. So here I got a arrow which represents acceleration. All right. So I'll skip the example today because it's time to end the class and come back to this tomorrow. Thank you very much.